Hello and welcome to iitiansgateclasses once again. So we have seen single linked list and many programs on single linked list, like reversing the single linked list and inserting a node in single linked list, inserting a node at the beginning at a given position or at the end of the single linked list. And we have also seen a program where we have deleted some nodes, and the intuition is just manage the pointers. Okay, and sometimes you are given with a program and you have to track the pointers only, like what is next and what is there next. And you have to identify the loop in the linked list or mid pointer of the linked list. Like we have seen a program, binary search algorithm in linked list. And we have seen that it will take order of n, not order of log n. So it's better to do a linear search instead of doing the binary search. So binary search is not useful. And we have seen merge sort in the single linked list. So similarly, if I try to cover all the program on single linked list, there are many possible programs, or you can say many possible problems using single linked list that we can create. And we cannot cover all those things into this course. What we can cover here is like the intuition, like how to manage pointer or track pointers, how to iterate linked list, and what is the meaning of linked list, why it is required, what is the benefits of it over an array. We have seen all such things, right? So now we are moving to double linked list. We will see some program of the double linked list, some application of the double linked list, right? And before moving to double linked list, let's see what's the node, a single node. How can we create a single node in single linked list? It's struct node. So this is the definition of the node. Definition means in program we have to write it like this. Then we can allocate memory or initialize the node. It means we can insert the data into that node, and we can make links between these nodes. So if our data type is of type int, it means each node contains int type data. We will do int data. Okay. In data. Then we have one more thing, that is self pointer. So self pointer means it will point out to the same type of node. So this star indicates that this will refer a memory. So this is a pointer basically, and we will say next. So it will contain next node pointer of type struct node. Of type struct node, a pointer of type struct node. That's why it's called pointing out the same kind of data structure only, self-pointing pointer. Okay. But in double linked list, we have a pointer in backward direction also. Struct node. Here we have data. We have next pointer, similar to single linked list. Struct node star next. Struct node star, and we have one extra pointer, which is previous pointer, pre pointer. Okay, previous pointer. Now how it will look? It will look like this. Okay, we have one pointer here. Okay, let me give some memories also, so you will understand what is the meaning of the arrows. Okay, so for the first node, if first node have some data like 10 of type integer, here we will have null. So this is basically pre-pointer, not pre, it's pre. Pre means previous pointer, pointing out to the previous node. For the start pointer, there is no node before it, so the pre-pointer is basically null. This is next pointer. Okay, so then we have again one more node, have value 20, for example. This next will contain some value. For example, the starting address of this one is 1000. The starting address of this one is 2000. So it will contain 1000 here, 1000 here. Okay. Similarly, here it also have a pointer to the previous node. So it will contain 1000 here. And it will contain 2000. Sorry, it's not 1000. It is not 1000. It is actually 2000. Okay. So we have 2000 here. Okay, this arrow indicates that it's referring to this one. Okay, in computer program, in the physical memory, we cannot simply apply the arrow, right? Physical memory, your RAM or your disk, we cannot do this arrow structure. We have to save some address. Now we are denoting this node. So this is pre-pointer and this is next pointer. We are denoting these nodes. We are saying that, okay, starting at this 2000. That's why we have written 2000 here. Okay. I hope you get the this kind of things right now. Like how can a node points to the next pointer or the previous pointer. Now suppose we have one more node, 30 value, and here we have null because it will not have further pointers, but it have a if its starting pointer is 3000, the starting pointer is 3000. Okay, so here we will save 3000, and this node indicates back to this pointer, so it will save 2000 here. This is our previous pointer, this is our next pointer. Okay, this is how double linked list work. Okay, it will look like this. Now let's see some programs, some simple programs, so you understand like how can we work with this double linked list. Similar to the single linked list, the program will be same. Let me write the first program where our requirement is to insert a node X. Okay, we are denoting that node as X at the and O double linked list. DLL means linked list. I denoted linked list as LL and DLL means double linked list. So again, we have to create a node first. Okay. Sorry for this. Let me check my mic setup one more time. Okay, it's connected. So sorry. So in double linked list, we have to go to the basically the intuition is here we have pointers like this. We can go in both directions. Okay, suppose this is the last node null here. So we will go to this node by iterating like this. We'll go to this node. And here we have already allocated using malloc. If you remember, we have created a node in case of insertion using malloc, allocated memory to a node. And in this malloc function, what we do, we will do it like initialize its previous pointer. Its previous pointer will point out to the last node. And last node start pointer will point out to this node. Okay, this is very simple, right? First, you will create this node, initialize it. Before initializing, what do you need to do? First, allocate memory. First step is allocate memory. Allocate memory using malloc function. Okay. Second step is basically iterate through for doubly linked list, so DLL, and go to last node. Then third step is just set up the pointer, set up the pointers. Okay, this is the intuition, right? So first you will create this, you will initialize the memory, then you create this whatever value X is given, you will initialize the memory. First allocate the memory, then initialize it. Allocation of the memory means you have to occupy some space, right? It's like first you will look for the plot. Whenever you are trying to build a house, first you have to look for the plot, right? Then only you can build the house. And then you can only go inside that house, right? So that's why we will first create a plot. We'll buy a plot here. Okay, then we will build a house and we'll move in. It means we initialize it. Okay, Then we will iterate through the linked list. This is the start pointer. We will iterate through the linked list, go to the last node and set up these pointers, right? These pointers. So let's write a program, C program here, because all pointers exist mostly in C, C++ language only these days. Java and Python don't have pointers concept. So we will say that first step is define struct node star p. This is, we have defined a node. Then we allocate some memory to it. Struct node star malloc. This is typecasting. Okay, and this is the allocation. Size of struct node. So it will basically allocate this much size. Okay, it will allocate this much size of the memory, using malloc function. Then it will typecast. First, this step will be performed. It will calculate the size. Then this step will be performed second. Then this step will be performed third step. Okay, this is how it will work. You should know about it. Okay. Then once the memory allocation is done, this is memory allocation. Then we will initialize it. Initialize it. Okay. What is initialization step? So this is our second step. This is our second step. This is our third step. Our third step is p data equal to x. Okay, p next equal to null. P pre. Now we have 2 pointers, so we have to initialize 2 pointers equal to null. Okay, so this is our 3 steps. Now the fourth step is, it's not equivalent to these steps. Okay, these are different. Right now we have done only this step. This one is done. Now we iterate. Okay, now we are performing the second step basically. I will perform it in the next page. We say while s next not equal to null, s equal to s next. Okay. So it will basically jump on to the last node. Using this loop, we will move to the last node where we have the next as null. Once we reach here, we will set up the pointer. So this is our basically fourth step till now. Fourth step means I'm going via these numbering 1, 2, 3, and 4. Our fifth step is basically the last step where we set up the pointers. You say as we are at last pointer, right? So we have to set it next as our newly created p. As next equal to p, and p should point out to this last node also. So p pre equal to s also. Okay, done. Now in the single linked list, I always told you that we always take temporary pointer, right? Like q, p, r, something like those, and we assign that s into those pointer, like q equal to s. Then we iterate in q. We will never iterate s, because once we lose s, we will lose our first node. Here, that's not going to happen because we can go back using pre-pointer. Okay, so if we do like this, if we iterate our starting pointer, then it can go back, right? It can go back also till the pre is null. The pre pointer is null. That will indicate the starting pointer. But still, I suggest you to use temporary variable because you don't have to come back again. You don't have to come back. It will consume time each time when you run some code. Your start pointer will move out to some middle pointer or some last pointer, and you have to go back again. That is why you should always use temporary pointer also here in the doubly linked list also. But it is possible. You will never lose your previous nodes because you have pre-pointer. Now let's solve one more example here. Our question is, again we have to insert a node with the data X before a node with data Y. Okay. So again, you will create this step will be, these three steps will be same. Okay. Again, you will create a node. Okay, let me write those again. So first you initialize like struct node star p. This is defining the pointer. Then you allocate memory to the pointer. Struct node star malloc size of struct node. Okay. Then you allocated memory to it. Then you initialize it. P dot data equal to X. P next equal to null. P pre equal to null. Okay. Once you've done these things, you have a pointer with data X. Now you have to find a node which point to Y. Okay. So our intuition is basically, suppose this is our linked list. This is our linked list. Here, this contains value Y. Right. Now, this is our P here. Here we have null initially. Here we have null initially. Okay. These two are null initially. Okay. Now, what do you need to do? You need to create two links that this P will point out to this one. The P next should point out to this one. Why? Because we have to insert this P, this node, just before Y. So this P should point out to this Y, the next pointer of P, and the previous pointer should point out to this one. This is one thing. Another thing is you need to break these two links, and the next pointer of this previous node where Y exists, the next pointer of this node should point out to P, and the previous pointer of Y should point out to P also. So here you have to basically reset 4 links. Two links are new, and 2 links you have to reinitialize. Like these 2 links you have to break and initialize these 2 links. So that's what we need to do. So first we'll iterate and reach till here, and we can do all these things. Let's do. How can we do it? Let's see. While S is our start pointer, S data not equal to Y, and S next not equal to null. So S data not equal to Y, it says that, okay, if the linked list, the doubly linked list have the value, have data Y, then we will reach out to that pointer, means this pointer. We'll reach out to this point, this node. We'll reach out to this node if linked list have the value Y. If it don't have value Y, then this will make us safe. Else we will get null pointer exception, and we don't want to do that. Why? If we iterate through our double linked list and these two the null, will get an error that we are pointing to a null memory. For example, if we iterate through the whole linked list and if we reach here, again, there is no node here, it's null. And if we do, null next, it will give us error. Okay, error. That null don't have next pointer, right? So you don't want to go beyond this last pointer. That is why this condition will make us safe. And you will do s equal to s next. Now, two things can happen after this loop. This loop have ended here. Either we reach to the node y, node which contains value y, or we reach to null. Okay, or we reach to the last node, not null. It's saying next node equal to null. Next node equal to null. It means we will reach to the last node. So if s next equal null and s data not equal to y, it means that linked list don't contain a node that have value y. So we cannot insert because we have to insert just before y. So there is no node which contains value y. So we can simply return. You can say that, okay, this is not possible. Now, if we haven't returned from here, it means we have reached to the node which contains value y. Okay. So what we can do? We can simply say p. Okay. Now let's remember what we did. We had two new links, this one and this one. Okay. So right now we are here. So let me create one more link list. It will be clear for me. We are here now. Okay. And we have a new node P which contains X. Now what can we do? First, we need to point P pre. It's not double E, it's single E. Okay. P pre, previous pointer of P to Y pre. Okay. I hope you got it. This is what? This is what? Y pre, right? The address of this node is basically Y pre. Here we contain the address of this node, right? So P pre equal to Y pre. So this link will be made. Now P next is what? Y. Now this link will be made. Not Y, sorry. It's not Y, it's S actually. Sorry. S. Y is the value of the node. So it should be pointer S. S pre. Not S pre, S. Okay. So P pre should, it's not Y pre, it's S pre. S arrow pre. S arrow pre. Okay, so this is S node, node S. We have reached to S node using this loop, right? And in this condition, we know that we have reached to this S. Now, P, previous pointer of P should point out to the previous node of S. So this condition will do this. Now, the next pointer of P should point out to S, right? S. Okay, so these two, I hope you understand these two things. Now, the next thing is the previous pointer, this previous value. What is the previous value? Suppose Y, sorry, not Y. We have a pointer Q. Let's assume this is Q. This is Q. So what is Q right now? Q is what? Q is S pre right now. This is Q. And what do we need? We need this Q to point. Q next pointer we need to point here. Okay. And how we can say this Q will point out to P. It's S pre next. S pre next will point out to P, and S pre equal to P. So this S pre will point out to P. Okay, let me write down these 4 things again. What did we do here? You need to understand this program very clearly so that you can insert a node in between any 2 nodes, right? Right now, for S is here. This is S pre. Okay, S pre means this is the node, actually, this is the node address. S pre is the node address. S pre is the node address, or you can say node pointer. This is the node pointer. And here we have a new, we have a new node with value X. And both contains null here. This is P. First, we will point this out to here. How can we establish this link? We will say that P pre equal to S pre. Okay. Then we say that, okay, this should point out to this one. Now we say that S pre, not S pre, P next equal to S. Okay, these 2 links are created. Now we want to remove this link. And we want this node to point out to this node. It means S pre next should point out to P. S pre next should point out to P, right? And we want this link to be created again, such that S pre should point out to P. S pre should point out to P. This is how we can create links, and that's it. Okay. Now, what if we want to create, if we want to delete a node? Okay, if we want to delete a node, suppose we want to delete a node. Okay, so you want to delete a node which contains data Y. So we iterate, we again say that, okay, let's apply the loop, apply this loop, iterate such that while this is S right now, S data not equal to Y and S next not equal to null. Either we will reach to the last node or we reach to the data node. Last node could also be the data node. Okay, last node could also be the data node. So we don't have to worry about it. This condition will take care of it. We'll do S equal to S next. Once we reach to this node, or S will reach here. S will reach here, right? Now we need to delete this one. How can you delete this one? You will say that S pre, you can check condition here. If S data equal Y, it means now we have reached to this one and we are not to the last node or the node where it don't have the data. Using this condition, you can satisfy that and that you have reached to or desired node. Okay. Now what do you need to do? S pre should point out to S pre. Let me use another color. This is S pre, right? This is S pre, or pointer to this node. Pointer to this node. S pre is the pointer to this node, right? Its next is right now pointing to S. It should point out to S next. S next is this one, right? S pre next should point out to S next. Right now, S pre means this node. S pre node is pointing out to S right now. Okay, this link. So we break this link and we say that, okay, point directly to this node, which is S next. This is S next. Okay, S next. Similarly, the previous pointer of S next. Right now, what is S next? S next. This node's pointer, previous pointer, is right now pointing out to S3. It should point out to. Right now, the previous pointer of S next is pointing out to S, right? This pointer. We are breaking this pointer and we are saying that let's point here. Okay, S3. Try to pause the video and understand this. Okay, pause the video and try to understand this, that what we are doing, we are going to this node and we are saying that its next pointer is right now pointing to S. Just skip it. Just skip the current node and point out to X next. And its next pointer, its next node is pointing out to S in the previous pointer. And we are making it pointing to the previous node using SP. Using these two conditions, you can basically delete a node. This is how you can insert and delete a node. Now, what is a circular double linked list? This is one more variation of the linked list. Circular double linked list is basically represented using the same node structure. Same node structure, right? This node structure. We have a data pointer, we have next pointer and the previous pointer. But the difference is at the end of the linked list, at the end of the linked list. Previously in the double linked list, we have null here, right? We have null here. And we have null here. In the previous pointer of the first node, we have null. In the next pointer of the last node, we have null here, right? So what we are saying is, instead of having null, the next pointer will point out to, next pointer of the last node will point out to the first node. And the previous pointer of the first node will point out to the last node. So this will become a circle, right? And what is the benefit? Like, if you want to go from first node to the last node, you can instead of taking order of n time, because in the previous double linked list or single linked list, you have to go here like this, right? Now you can simply use this pointer, and in order of one you can reach. In linked list or double linked list, reaching from first node to the last node will take order of n time. Here it will take order of 1 time. That's it. And you can similarly see that all the program will be same, all the code will be same. Okay, now let's see what is binary tree. Binary tree is basically application of double linked list. How double linked list? So we had previous and next pointer, right? We had previous and next pointer. Now the binary tree will look like this. Instead of previous and next pointer, we have here the left child pointer. Here we have one more node. This is our root. Okay, or root pointer, or you can say start pointer. So in binary tree, we always have a root pointer in our hand. From root, we can reach to any other node. But if we have a pointer to some leaf node or some intermediate node, we can go back to our root. So that is why we will always have a root pointer. Okay, now this is our left children. This is our right children. Similarly, this is our left children. This is our right children. So this is how you can create binary tree. Binary tree means at max 2 nodes. So you can have something like this. Binary tree means at max 2 children. Sorry. At max 2 children. Okay, binary tree means at max 2 children. So here, if we have a let me use some other color. A, B, C, D, E, F. G H. Okay. And the address of root node is 1000. And here we have address of this node is 2000, 3000, 4000, 5000, 6000, 7000, 8000. So in the left part, left pointer, here we have address 2000. Here we have address 3000. Okay, it's pointing out to this node. Here we have 4000 here. Here we have 5000. Here we have 6000, 7000 here. Here we have nothing, null. Okay. So this null is saying that if on the both sides, left and right, we have null, it means it's a leaf node. It don't have any children, not even a single children it has. Okay. So here we have 8000. So this is not a leaf node. Here we have null. Okay, so this is our binary tree. Now you can assume that once we create, we have similar node structure, binary tree, like this. We have similar node structure, right? So instead of next and pre, we will name that as left and right. Okay, this is the pointer to the left children. This is the pointer to the right children. And we can make a tree for struct node. So now this node is basically binary tree node. Int, for example, if our data type in the binary tree is of type int, we will say int data struct node star left struct node star right. Okay, so using this user defined data type, structure is a user defined data type, right? We can create binary tree. So this is a single node, and replicating these nodes and connecting, like establishing a connection between them, we can create a tree. So that is why binary tree is an application of double linked list. Okay, so what if somebody asks you to have some program? Okay, let me give an example. If we want a, what do we want? We want to count number of leaf nodes in binary tree. So how can you count? Basically, I will tell you the recursive program, okay, recursive function. But the intuition is that once we reach to a node which don't have left or right pointer, that can be called as a leaf pointer, leaf node. So it will return 1. Okay, it will return 1 to the parent. Now binary tree can also be made like this, right? So it is a right skew tree. Null here, null here. So here we have null here, null here, null here, right? We are having only the right children at each node. So this is right skewed. So this is skewed, okay? Now you have n pointers and n levels. That is why it's skewed. But you have only one leaf node, only one leaf node. Only one leaf node here, right? So how can you count number of leaf nodes in a binary tree? Let me try to write a very simple program for it. We will define a function. We will call count leaves. Count leaves, okay? And we will pass the root in it. Struct node star root, okay? Now, if this root is null, root equal null. If this root is null, okay, we will return 0. it means there is no further node or current node itself is null. So we cannot do anything, we will return 0. Right? If this root left pointer is equal null and root right pointer is also equal null, then in this case, this is a leaf node. Okay, this is a leaf node. So it will return 1 here. It will return 1, exactly 1. So right now we are iterating, or you can say recursively reaching to the leaf node, and the leaf node don't have any children, then it can return 1 to its parent function. Parent function 1 means whoever called this function. Now, if that is not the case, either we have a leaf node or either we have a left children or right children, then in that case, if this is not the case, it means it is an internal node, right? And in case of internal node, we will do something like this. You say that, okay, integer xl. So this is a variable which contains count of left subtree leaf node. Left subtree leaf node. Once the recursion is done, this will have left subtree leaf node count. So we'll call the same function because it's recursion. If you don't know what is recursion, go back to the algorithm post, check it out. Now we will call the same function again, this count leaf function again. And pass root left here. Okay, root left here. Similarly, XR will have right subtree, note the node I'm saying, right subtree count of nodes. So we will call count leaves the same function recursively root right. Okay. Now at the current node, for example, current node is some intermediate node. At the current node, what is the total count? It is return XL plus XR. Okay, XL plus XR. And current node cannot be the part of leaf node. Okay, because we have already checked here and we have returned if current node is the leaf node. So we'll return XL plus XR. Try to understand this program because based on this program, I will construct many other programs, many other coding questions. What we are doing here is we are recursively calling a function. Recursive function means at each node, this function will be called. At each node, this function will be called recursively. Let me try to make you understand here. This is our root. Here we have children. Something like this we have. Now, how many leaves do we have? We have 1, 2, 3, and 4 leaves. We called this count leaf function at the root, CL, count leaf function at the root. We called count leaf function at the root. So this function has to be solved many times. Now, once we call this count leaf function at the root, what will happen? Check this function. It will say that root equal null. Okay, root is not null. Here root is not null. Okay, this root is not null, obviously. And it's saying that root left equal null and root right equal null. Then in that case, return 1. Now you can see that root left is not null. It's pointing out to a node. Root right is also not null. So it's pointing out to the right node. So this condition is also failed. This condition is failed. This condition is failed at root. Now it will say that, okay, call the same function again, count leaf function, with passing root left. Instead of root, we pass root left. Now this same function will be called. This same function will be called here, count left. Similarly, the same function will be called here, count left, count left. Right now, no function, no node have returned anything. There is no node which have returned anything. Similarly, this will also call count L here. This will also call, let me try to write in the calling order. This will be called later on. Okay. Right now it's calling like this. If you remember algorithm course, I told you that the calling order is root, left, right. This is the calling order, okay? Root, left, right. Root, left, right. So at the root, we have called the function. Then at the root, then root, then root. Then we'll check. At the root, then we call left. This will be considered as root, then we call left. So this is the calling order. And what is the returning order? Left, right, root. This is the returning. First, the left function will be solved. Then the right function will be solved. Then the result will be returned to the root. And the root will solve it itself and return it. That is how the calculation is done. That is how the calculation is done. Okay, I have covered this part in algorithm. Still, I'm covering it so that you don't get confused in the previous code. Now, what's happening here? Once we call CL here this is also null, left is null, this is null. So it will return 1 here. It will return 1 here. And this 1 will be saved. Here we have variable. Like in the instance of this function, we have variable XL and XR. And XL, it will save 1. In XL, it will save 1. I'm talking about this node, right? This specific node. This specific node have a variable XL and XR. If you don't understand it, open up this page. I'm solving the question using that tree. Okay. Open up this page and try to understand what will be saved in the XL. In XL, we will have 1 down. Now there is no XR, right? So it will still call the same function, CL function, and pass null limit. It will still call for right. There is no node. But we have seen that in case of null, we are returning 0. So it will return 0 here. It will return 0 here. XR will have 0 here. And what this whole node will return? It will return sum of these two, which is 1. Sum of these two. Okay, we are returning sum of these two. So we return 1 here. Once we return 1 here, in the variable XL, it will save 1. After saving 1 in the XL, it will call, after the value of XL is calculated, it will call count leaf on the right node. Okay, it will call count leaf on the right node. Now here, it don't have left node or left children or right children. It's null. Okay, both are null. So it will return 1. It will return 1. And this 1 will be saved in XR. 1 will be saved in XR. And this node will return summation of these two, which is 2. So this node will return 2 at the root. And this 2 will be saved at the root in XL. In the XL, right? In the XL, it will be saved as 2. Now, for the right node, it will be called. Okay, so let me construct a sample tree and let me tell you how functions returns. How function returns, what is their return behavior. For example, if this is a tree, it will return like this. Okay, it will go like this. First, this left node will return. Then this right node will return. Then this node will return here. And this is the way I'm going down is the calling order. The way I'm going up is the return order. So now this will return. This node will return. Then this node will return here. Okay, and then this node will return here. So once we have all the values from left subtree, so this is left subtree for root, right? For root, this is the left subtree. Then this will call the right node. The way I'm going down is the calling order. The way I'm going up is basically return order. Then this node will return. This node will return here. Then this node will return here. Then this node will return here. Then the whole result of the right subtree will be returned, and we calculate the sum. So the similar way I have calculated on the left subtree, the similar way it will be calculated on the right subtree. This is very, very, very important. Okay. In any case, wherever you are doing some coding sample or anything, the function calling order and return order should be clear. Okay. The return order is the post order, and the calling order is, I think it's pre-order. Sorry, root left, right. Yeah. So it's in order. Yeah. I think it's pre-order. Yeah, pre-order. Root left, right is pre-order. So the calling order is calling order function, recursive function I'm saying is root left, right. And the return order is left, right, and then root. Okay, so this is post order and this is, I think, pre-order. Yes. Now let's move on to the next program, where using the previous reference, remember this code, keep it handy. I will be making a very small change, and we will calculate total number of nodes. Total number of nodes we are going to calculate by making a very simple change, by adding +1 here. And we will calculate total number of nodes. Now what we did here, right? Just we did +1 here. So this 1 is for internal node. This one was for leaf node. Okay, it's saying left equal null, right equal null, both are null. Left and right, both pointers are null. It means it's a leaf node and we returned 1. Here we did XL plus XR plus 1. Using only very simple thing by adding just 1 here. It says that these are left and right subtree nodes, and this is myself, my current node, and I am a internal node. This +1 says that we are at internal node, and this is the summation of left and right subtree number of nodes. Okay, you can again run the same program on this tree, or you can construct your own tree. Try to run this using this order, this pre-order and post-order thing, the way I have constructed this red line. Okay, the way I'm going down is the coding order, the way I'm going up is the returning order. Okay, I have repeated several times. Now this is what node count leaf. So let me write the clear program for you, which is count nodes. I'm counting all the nodes in the tree. Okay, struct node star root. Okay, so let's see if our root is null. Basically, just return 0. It means that it's a null. We have reached to the null pointer. There's nothing there. It's the current node is null. So there's no node basically. So we are returning 0. If root left equal null and root right equal null, it means we have reached to the leaf node. There is no further node after it. So we have to return the count for the current node. The count for the current node is 1. Okay. Now let's calculate left subtree. This is indicating leaf node. Now, if we are not at the leaf node, we are at some intermediate node. The count for the left subtree is we'll call the same function count node root left. Okay. So we have called the same function for the left subtree by passing left subtree root. What is left subtree root? Okay. So if this is the case, right now this is the root of whole tree. Now if we recursively count for this tree, this is the left subtree root. So we'll call for this. Okay. Similarly for right one, count nodes root right. Okay. So we have called for the right node or right tree also, right? Now in the leaf node, we don't want to count the current node. Why? Because if we reach to this step, it means the current node is an internal node, right? Because we could have returned from this node. If we had returned from this step, it means we are at the leaf node, right? If we haven't returned the function from this step, it means we are at the internal node. So if we also want to count the internal node, so we return xl plus xr plus 1 here. Okay, in the previous example, we haven't returned 1 here because we don't want to count the internal node. Here we want to count the internal node, that's why we pass 1 here. Right? So now let's see one more example using a little modification here. Okay, we will see further example later on. Okay. So, okay, let's see one more small modification where we want to count only internal nodes, only internal node. Try to pause the video, try to guess it, like what is the recursive solution for that? How can I make a little change in this program and we can count only internal nodes? Try to pause it, try to guess it, or try to figure it out. Let me give you the solution for it. Here, if you haven't figured it out, let's hear my solution. Here, if we say that, okay, count internal node, the whole structure will be same, except we'll pass 0 here. Because in case of leaf node, we don't want to count it, so we'll pass 0 here. And the whole program will remain same. So we have seen the program for leaf node, internal node, and total node. Okay, recursive program. It's a very small, concise code. You can see the number of lines: 1, 2, 3, 4, 5, 6, 7 lines. Within 7 lines, we have seen three solutions. Okay. Now let's calculate its time complexity. So if a tree is balanced, what is the worst case? The worst case in this case, counting the node, is that our nodes are maximum, right? Whether leaf node or internal node or low node should be maximum. If we are counting nodes, what is the worst case scenario? That our nodes are maximum. It means all internal node have 2 nodes. Okay, like this complete tree-like structure. The worst case scenario in our case is each node have exactly 2 children, each internal node, and leaf node don't have any children, right? So that is the worst case for counting nodes. If our nodes are maximum, then this is our worst case, right? Then in that case, how many nodes lies at the left? N by 2. How many nodes lies at the right? N by 2. Right? Almost N by 2 because it's basically N minus 1 by 2. N minus 1 by 2. But we can avoid minus 1. If N is 2 views, it's basically N by 2, N by 2. In the current node, if we exclude. So it's N by 2, N by 2. So it's not N by 2. For internal nodes, we can, if we have seen the recurrence solutions, I always indicate the recursive solution as this T. Is T N by 2. It's again T N by 2. So what is our solution? Except T N by 2, what is our effort? Is order of 1, right? Nothing, there is nothing that we are calculating. So recurrence relation here is 2Tn by 2 plus 1 for counting the nodes. It's 2Tn by 2 plus 1 or plus how constant you can assume. And once you solve it using any theorem like master theorem or any substitution method or recursive tree method, you will see that it's actually order of n. So to count the using this recursive solution, the effort is, because you are going for each node. If you have n number of nodes, you are going to each node, right? You're calling the function. So obviously it's order of n. If you apply recursive tree method, okay, you will see that it's order of n. But this is the recurrence relation. Remember this: 2tn by 2 plus 1 or plus c. Sometimes it's c. It's the same thing. One is c can be represented as 1 if n value is too huge. Okay, so in the next lecture, we will see some more program like calculating height and calculating number of levels and like balancing out the tree, binary search tree, deletion in the binary search tree, some programs for that, balancing out the tree and rotations. How can we balance out the tree? Almost balance out the tree. Okay, what is balanced BST, AVL tree, something like that. We will try to see in the further lectures. This tree topic is actually quite easy. If you understand recursion and if you have correctly understood double linked list, it's quite easy for you. Thank you all for joining. I will see you in the next lecture. Thank you.